time of concentration is arguably one of the most important characteristics of a watershed. It helps us to move from effective rainfall intensity or a hyetograph to your hydrograph, to unit hydrograph. So what is time of concentration? Well, the definition, I have two definitions for you. One of them is over here. This is a standard definition of time of concentration that tells you that TC, or time of concentration, is the longest travel time that it takes for a surface runoff to reach the watershed outlet. This is the standard definition, although this is a little bit more this definition makes time of concentration simple. It's way more complicated. That's why I have the second definition over here for you from David Maidment in 1993. This is my favorite definition. And specifically, I want to focus on the red part, the part that is underlined. This definition tells you that the remoteness in time of concentration relates to the travel time rather than distance. In other words, distance is only one variable in determining time of concentration. There are other variables that are important in figuring out and determining time of concentration. What are those? Effective rainfall intensity, length, slope, and other characteristics of a watershed, like land use and land cover, roughness, so on and so forth. So in order to accurately determine time of concentration, you need to have an accurate representation of these variables that I just told you as well. But how do they impact time of concentration? Some of them are really easy to understand. For example, slope. Let's say that every other characteristics of two watersheds are exactly the same except for slope. One of them has a higher slope, the other one has lower slope. If I ask you that I have a drop of water in a watershed and this drop of water is going to make it to the outlet of the watershed, for which watershed this drop of water is going to make it to the outlet faster, you are going to tell me that if all the other characteristics are exactly the same, the watershed that has a higher slope will eventually have higher time of concentration. The water is going to reach the outlet faster. Similarly, for length, what is important is the length of the river, for example, the main channel that you have, right? Why is it important? Let's say that you have a watershed like this. Actually, you have two identical watersheds. Everything else is the same in the watershed except for the length. Well, the length of this river is like this and very straight. The length of the other river in the other identical watershed is like this. In other words, the river is tortuous. That's one of my favorite words. English is not my first language, so I like to learn different new words. So tortuous is the word that I want to introduce over here. All right, it's a noun. Tortuous means that there are lots of twists and turns. So in turn, when you have a lot of twists and turns, and when the watershed is tortuous, then it's going to take a longer time for water to reach the outlet of the watershed. Okay. There are many, many different ways to calculate time of concentration. I have some of the more famous ways and equations of calculating time of concentration on this slide. A more complete list can be found in your textbook. And if you're watching this video, you can just search different ways of calculating time of concentration to see a very long list of different methods. But I want to mention that there are two methods that are more popular than the others. At least I can say that in the United States. The NRCS velocity method and the NRCS watershed lag method are by far more popular than other methods. The velocity method, the NRCS velocity method, is also known as TR55 method because in technical report number 55, there is the procedure on how to calculate time of concentration using this method. And the NRCS watershed lag method is developed for watersheds that you don't have a lot of detailed information about, and you want to calculate time of concentration based off very simple characteristics of a watershed, such as slope and length of the river, for example. Okay, so in this video, I'm going to talk about the two NRCS methods, TR55 and the lag method. And I highly encourage you to take a look at the variables and parameters in other methods as well, because some of these methods are specifically developed for specific use cases. For example, U.S. Federal Highway Administration has its own equations for calculating time of concentration that have been calibrated and validated in different highways in the U.S. Okay, so I want to introduce you to NRCS velocity method, or the TR55 method. This method tells you that time of concentration can be divided or separated into three different times. The blue one over here is called sheet flow time, and then you have shallow concentrated flow time, and then you have channel flow time. In other words, this method defines three different flow regimes: sheet flow, shallow concentrated, and channel flow. Now let's talk about the characteristics of these three different flow regimes. Sheet flow usually happens in the headwaters of your basin or watersheds. Okay, this happens near the ridge lines for the first 50 to 100 feet that overland flow is formed. Shallow concentrated flow is defined as the type of flow regime that happens after sheet flow and has the maximum depth of 0.1 to 0.5 feet. Okay, and the important thing is that whenever you have shallow concentrated flow, you cannot define the channel. There's no defined channel when you have shallow concentrated flow regime. And then beyond that, beyond shallow concentrated flow, you have your channel flow. Channel flow is defined by NRCS, where you can see from aerial photographs, you can see the channel. So the channels are visible. And whenever you have channel flow, you need to have basic understanding of how the cross-section of channel is defined as well to be able to calculate the time related to channel flow as well. So these are basic characteristics. So if I were you, I would remember this number. This would be when overland flow starts generating within 50 to 100 feet from the ridge lines of the watershed. That would be sheet flow. When the depth of water is less than or in between 0.1 and 0.5, or the maximum depth of water is that, this is your shallow concentrated flow. And when you have channels, you have channel flow. If you calculate all these three times, the summation of these will give you your time of concentration. Let's take a look at the equations for sheet flow regime and how we can calculate the time for sheet flow. All right, so this equation is recommended by NRCS. It has some familiar variables in it. P24, right over here, this you can find from NOAA Atlas 14. This is the 24-hour rainfall, and the return period that should be used for this is a 2-year return period. However, in many practical applications, it is recommended to use the return period that matches your design criteria. And the other thing that I want to talk about is this N over here in the numerator is the Manning's roughness for the surface. L is the length of the flow, S is slope, and C is a runoff coefficient, runoff constant that varies from 0.42 to 5.5. NRCS recommends the value of 1, and if you take a look at the equations, you can tell that whenever C goes higher and higher, whenever C increases, time decreases, okay, because it's in the denominator of that fraction. Okay, there are limitations to this equation. This equation specifically was developed for type 2 and type 3 rainfalls. So you probably are familiar with SCS, rainfall types and zones. This equation was developed for type 2 and type 3 rainfalls. If the area that you're calculating sheet flow regime time for is located in type 1 or any other types, you need to use a separate set of equations to calculate T sub SF. And the other thing that I want to mention, and before that, I'm going to show you that set of equations as well. Another thing that I want to mention is everything that I told you has the units in SI system. What if you want to use US customary system of units? If you're doing that, here are the changes that you need to do. So P24, the 24-hour 2-year rainfall should be in inches, and your length, the full length, should be in feet. So we can change these two, and that would be it. The other variables are dimensionless. For example, slope doesn't have any dimensions, managed roughness doesn't have any dimensions, and C is dimensionless as well. And the table that you can see on your screens will give you the equations for different zones, not just 2 and 3, but all the SCS rainfall types that you have. Notice that this is the logarithm, natural logarithm ln over here. And in order to use this equation, you need to calculate this variable n. And this variable n is based on the characteristics that we defined in the previous slide. C was your runoff constant, S was slope, N was manning roughness, L was length. And then in addition to that, you have 3 parameters, A, B, and C. And you can find that A, B, and C over here for each rainfall type. For example, for type 1, A can be calculated using this equation that takes into account P24. B is a constant and C is a constant over here. So if you put all of those into this equation, it eventually gives you natural logarithm of T sub SF, and then you can calculate T sub SF from the equation. So if your study area is not in type 2 and type 3 rainfall zones, you need to use this table to use the right equation for your study area. And just quickly, I want to mention that for Manning's roughness, there are tables in different drainage manuals in different states, and even ASCE has a manual that gives you roughness for different surfaces. I have copied and pasted just parts of that table over here to tell you that it has a recommended range, and it gives you a recommended Manning roughness as well. After learning about sheet flow, now let's learn about shallow concentrated flow regime. In order to calculate the time for shallow concentrated flow, we're going to use the physical equation for time. Time is the length divided by velocity. Length can be determined using different GIS software packages. And then velocity is the thing that we need to figure out. We can tell that velocity is a function of slope of the shallow concentrated flow, or S sub SC, and a function of K. This K is called intercept coefficient. And this intercept coefficient has the units of meters per second and is defined based on the land cover and flow regime as well. So there are tables and nomographs that Federal Highway Administration, ASCE, and Drainage Manual of different states publish that tell you, depending on the land cover that you have, what would be the value of K that you can consider to calculate velocity for shallow concentrated flow. And once you have that velocity, you can put it into this first equation over here and calculate time for shallow concentrated flow. Okay, so very simple equation. You highly depend on nomographs and tables available in different sources to calculate K, and then velocity, and then time. Last but not least, I want to talk about channel flow regime. If you have had any hydraulics course, this equation should be very familiar for you. This is Manning's equation that gives you velocity. If you are using SI units, you are going to use this equation. If you're not using SI units, instead of having 1 in the equation, you could change that conversion factor to 1.49. So 1 should be 1.49 to have Manning's equation in US customary system of units. Again, time is calculated using its physical definition, length divided by velocity. Now, here, because we have a channel, because we have a defined open channel, we can calculate velocity of the channel using Manning's equation. And in Manning's equation, N represents the Manning's roughness that I showed you how you can find for different land covers. R is hydraulic radius. This R over here, the point is that the R is the hydraulic radius of channel at bank full condition. This condition that we have over here is bank full condition, and these two over here are the channel banks. Okay, now how do you define hydraulic radius? R is defined as cross-sectional area of the bank full condition divided by P, which is wetted perimeter. So if I want to show you, the cross-sectional area would be this. And if I want to show you wetted perimeter for this channel would be this line that I am going over. So this is the wetted perimeter of the bank full condition. So this length, in other words, the units for wetted perimeter are units of length, such as feet, and the units for area is going to be square feet, for example. Okay, so the unit for hydraulic radius would be units of length. Okay, this is how you calculate hydraulic radius, and S sub CH is the slope of the channel. Using all these information, you can calculate time for channel flow. Now, the question is, you all know that if you have a channel, the channel has an irregular cross-section. If you have surveyed data for the cross-section, you can enter that. If you have a digital elevation model that gives you the channel cross-section, you can enter that. Or sometimes it is acceptable to assume a shape for your channel. Let's say maybe your channel can be assumed to be half of a circle, or maybe your channel can be assumed to be a trapezoidal channels, open channel, so on and so forth. So depending on what the condition of your study area is, sometimes it is acceptable to simplify and consider an irregular channel, a regular or prismatic channel. So far we have learned about NRCS velocity method, aka TR55 method. Now I'm going to introduce you to NRCS watershed lag method, which is way easier to calculate because it only depends on watershed physical characteristics that are readily available to us. So in other words, we don't need to decide on the flow regime. Okay, so this method uses only one empirical equation that I have written right over here to calculate time of concentration in hours. This is important that time of concentration from this equation is in hours. L is the length of flow. S sub 0 is the slope, average slope of your basin. And the other variable over here is S. S is related to the SCS curve number method. The terminology that we use for S is potential maximum retention. In some textbooks, you have another name. You have maximum watershed storage. These are synonymous. Okay, what is S? S is related to a curve number. And again, all the units that I'm using are in SI. Curve number depends on the land use, hydrologic soil group, and the hydrologic condition of your watershed. So based on these three factors that I told you, each basin will have one value of curve number. When the curve number is low, that means that a lot of your rainfall is going to be converted to infiltration, and when curve number is high, a lot of the rainfall is going to run off the surface, aka generating surface runoff. So in urban areas, higher curve number results in higher surface runoff. Okay, so once you have that curve number, that can be determined based on GIS calculations as well. You can calculate the value of S, potential maximum retention, and then S goes into this equation, and the only two watershed characteristics that you need in addition to S are slope and flow length. And you can calculate a good estimate for time of concentration. You can see that this method is way easier computationally to calculate, to have an estimate for time of concentration. However, if you want to compare the accuracy of this method and the accuracy of the velocity or TR55 method, obviously the TR55 method is more accurate. The reason for that is that in TR55 method, you are separating different types of flow in a watershed. However, there are conditions that you might not be able to make a deterministic decision on what is a sheet flow, what is a shallow concentrated flow. So on those conditions, and if the watershed is small, it is acceptable to use the watershed lag method as well. I'm going to end this presentation by talking about limitations of time of concentration formulas and equations. It is important to know that every empirical equation that has been developed for a range of input data. In our case, time of concentration. All these agencies and people who have developed different equations, different empirical equations for time of concentration, have used a set of data to validate and calibrate their models. If you are using that equation for a watershed that has area, slope, so on and so forth, out of the range of the original data that was used for developing those equations, you are going to have numbers that are not valid. Why? Because you have violated the original assumptions of the model. So the first thing that I want to tell you is always consider the limitations of the formulas. If you're using the NRCS velocity method, TR55, go back to TR55 and see what are the limitations, what are the slopes that were considered in that method, and check the slope of your watershed and see if that slope is in the range of the slope of the original formula. If it is, you can use that with confidence. If it's not, then you need to look for a formula, equation, that has the slope that matches your slope. In general, majority of the equations that I showed you are developed for moderate slopes. So if you have a slope that is less than 0.1%, then you cannot use those equations to find time of concentration. And you need to use another equation, find another equation that considers that low slope. For example, this equation that was published in 2014 by KC and other colleagues. I have the original paper over here if you are interested to take a look at it. This was specifically developed for the slopes that are less than 0.1%. The other thing that I want to talk about is operator variability. If you want to calculate time of concentration using the TR55 method, you need to make a lot of decisions. What is considered as shallow concentrated flow? What is considered as sheet flow? So on and so forth. What's the value of roughness over here? How to define the bed of the channel? So on and so forth. All of these decisions are your decisions as an engineer. However, if you give the same project to another engineer, their decision might be different from yours. So depending on who calculates time of concentration, you might come up with different values for time of concentration. As a matter of fact, in 2007, Feng and colleagues did an experiment. They actually had 3 teams of engineers calculating time of concentration using TR55 method. And the results were really interesting. I have linked the paper over here. If you want to take a look at it, just search the title and you can access the paper. The results were really interesting. The results show that there is a significant variability in time of concentration and how different teams calculated time of concentration for the same watersheds. There are summaries and statistics shown in the paper that I'm not going to talk about over here. What I want to tell you that be aware of these variabilities, the operator variabilities, because the decision that I make as an engineer might not be exactly the decision that you make as an engineer. Some other methods, other empirical methods such as the NRCS lag method, reduces this operator variability. Why? Because watershed slope is just one number that you can calculate using a digital elevation model and a GIS software package. Length is something, again, you can calculate using a GIS software package. So there are less decision making involved in the process of time of concentration determination using methods that are more empirical. And the last thing that I want to mention is you need to be aware that all of these methods are empirical methods and they have errors. Specifically, there was a study, again, that I have linked over here. They used 11 different formulas to calculate time of concentration for 48 urban watersheds in the US. The results was really interesting. They showed that for more than 50% of the watersheds, the catchments that they considered, the error for time of concentration, for estimated time of concentration, was more than 30 minutes or half an hour. This is very, very long. So what I want to highlight over here by giving you all these limitations and uncertainty is that it's a good practice to, instead of relying on only one method for calculating time of concentration, focus on at least 3 different methods. And these 3 numbers will give you an idea of how big the variation between different formulas and different equations are. If they are relatively close, that tells you that probably in your study area, the uncertainty of determining time of concentration is low. But if they are significantly different, then you need to think about how you want to present this uncertainty in the report that you are writing. All right. This is our presentation about time of concentration. Let me know in the comment section the questions that you have and what else do you want to learn about time characteristics of a watershed.